Welcome back. Hopefully by now you've watched the last video where I talk about Uncle Tom's method for square root approximation and why it works. If you enjoyed that one, in this one I'm going to talk a little bit about how well it works, and specifically where it works well and where it doesn't work as well, and how you can do even better if you want to get even better approximations. So do you remember in the last talk we had this picture where we're trying to estimate the square root of 17. And our strategy to do that was to ignore this little square in the upper right-hand corner. We computed the area of the rest of the yellow parts and set that area equal to 1. That was the area of the yellow rectangles was 8 times x, and so we set x equal to 1/8 so that the overall area of that shape would have an area of 17. So 4 plus x, 4 and an eighth, was our approximation for the square root of 17. And it works very well. However, it's not perfect. If you take 4 and an eighth and square it, you're going to get the entire area of the box, including that small little box we ignored. And it turns out, because x was 1/8, the area of that box is going to be x squared, because it's x wide times x height, and so the area of that box is going to be 1 over 64. So 4 and an eighth squared is going to give you 17 and 1/64. And that's how much of an area we get with this process. If you're close to a number you know, like we were close to the square root of 16, we knew that was 4, then we kept x pretty small, and so the error was just a 1/64. But as you get farther away from square root you know, x can get as large as a half. If it gets larger than that, you should find another square root closer that you know. But if it gets up to a half, then the size of that box is going to be a half times a half, which is a quarter. So here's an example of the number that this approach does worst with, which is the square root of 2. To estimate the square root of 2, we would start with 1 and we'd add a half, because 1 plus 1 over 2 would give us 1.5. And so that's going to be our estimate for the square root of 2. But it's not a great estimate. The error, of course, is going to be x squared, because that's the size of the box, and that's going to be a half times a half, which is a quarter. And so 1.5 squared is really 2 1/4. It's not going to get you 2. Whereas the actual square root of 2 is 1.4142, and a lot of numbers after that. So what if we wanted to do even better? What if we thought that's not good enough for me? I want a rational approximation for the square root of 2, which is really good. Well, it turns out you can use Uncle Tom's method to do that too. The trick is you don't start with approximating from the square root of 1. Instead, you start with something much closer to 2. Now, what square root number do we know the square root of that's much closer to 2? Well, it turns out after our first step, we know the square root of 2 1/4, because we just computed it, and we know that 1.5 squared is 2 1/4. So let's start with 2 1/4, and this time we're going to go ahead and start with that number. And so to make this estimate, we're going to start with our base number of 1.5, and we know that we want to get to 2, not 2 1/4. And so just like we do when we're estimating more integer numbers, we know that we want to go down by 1/4, because the number we're targeting is 2, and that's 1/4 less than 2 1/4. So we're going to have to subtract 1/4 divided by 1.5 times 2, which is divided by 3. And so 1/4 divided by 3 is a 12th, and we need to subtract that from 1.5, or 1.5. And 1.5 minus a 12th is 1 5/12. And 1 5/12 gives us an estimate of 1.4166, which is much closer to the actual square root of 1.4142. So that's a trick you can use to get a slightly better approximation if you really want it. If you're watching this video, which is a little more advanced than the last one, you might enjoy this next page. This next page, I asked the question of, well, what if we wanted to approximate it again and again and again? How much better can we do? So if we start with 1 5/12, well, first of all, we know that 1 5/12 will give us an error of 1/12 squared, because 1/12 was our value of x. And so we know that 1 5/12 squared will actually be equal to 2 and 1/44, which is very close to 2. But if we wanted to do better, let's go ahead and use this approach again. Now, I've got some math written down here. It's a little complicated, but without going through all the details, our next approximation, if we started off with 1 and 5/12, our next approximation would be 1 and 169 408ths. Now that estimate gives us a square root of 1.4142156, and that's very close to 1.4142135. The first 6 digits are the same. And the error for that is just going to be 1 over 408 squared, and you take that number square root, and you're going to get pretty close to 2. There's a lot of zeros there before we get a number past 0. Just for fun, I did it one more time, and you do it again like that, and that approximation is accurate enough that on the calculator I used, the first 12 digits were the same. Turns out when you get to the 13th digit, they start to differ, but every time you use this approach, it turns out you will double the number of digits of accuracy you have. So that's a really good rational approximation for the square root of 2. And that's kind of where this algorithm takes us, and thanks for watching.